All right, let's talk about amines, and it says here that amines are derivatives of ammonia, and you would have learned the name and the structure of ammonia in Introduction to Chemistry 1. So NH3 is the formula for ammonia. You probably also remember its molecular geometry in that it is trigonal pyramidal. It says here that amines are the most important type of organic base found in nature. So in fact, amines are bases. Okay, so amines are bases. And it says here that we can consider amines like substituted ammonia. So it says here that R can be either aliphatic or aromatic. So if we were to take ammonia and replace one of the hydrogens with an R group, as is shown over here, we get an amine. This is called a primary amine because it only has one R group and two hydrogens. If we have two R groups and one hydrogen, we call that a secondary amine. And if we have three R groups and no hydrogens attached to our nitrogen, we call that a tertiary amine, and you probably guessed that anyway. Again, amines have that trigonal pyramidal structure. Now remember, the electron geometry of an amine is tetrahedral, but electron geometry considers bonds and lone pairs, right? We're considering bonds and lone pairs. And molecular geometry considers bonds only, and therefore it is trigonal pyramidal. Okay? Now that's what they're representing here in both of these structures of ammonia and an amine, but I think an even better way to do it is to do it in 3D like I had done it on the previous slide. So I'm going to show the lone pair and the first R group in the plane of the board or the plane of the screen, and then I'm going to have one R group going in the back like this and another R group coming out in front like that. And this is where molecular models can come in really handy to help us visualize and see the trigonal pyramid. On the first slide, I explained to you what a primary, secondary, and a tertiary amine was. And here we have some ball and stick models at the bottom of the page that show various primary, secondary, and tertiary amines. The first one is ammonia. So here's the ball and stick model of ammonia down here at the bottom. Of course, we leave lone pairs out of our ball and stick model. And then we have this molecule here called methanamine or methylamine, and it is a primary amine. I'll put the condensed structure down here. Then we have the next compound, which is dimethylamine or N-methylmethanamine. Kind of a mouthful, that one. Anyhow, I'll draw the structure or the condensed structure, or partially condensed structure, I guess, of N-methylamine or dimethylamine there. So it's a secondary amine. And then if we draw N-dimethylmethanamine, or an easier way of saying that is trimethylamine, we have a tertiary amine, and I'll draw the structure of that molecule right here. And don't forget your lone pair, which I left out here. In terms of physical properties, it says that amines form hydrogen bonds, but not as strongly as alcohols. And when we talked about hydrogen bonding before, we said the requirements for a hydrogen bond were to either have a bond between oxygen and hydrogen, nitrogen and hydrogen, or a bond between fluorine and hydrogen. And the reason why amines hydrogen bonds are not as strong as those of alcohols is just based off of the difference in electronegativity between oxygen and nitrogen. So if I look at an oxygen hydrogen bond, oxygen has an electronegativity of 3.5 and hydrogen has an electronegativity of 2.1. That's a difference of 1.4 units. If I compare the nitrogen-hydrogen bond, nitrogen has an electronegativity of 3 and hydrogen, of course, is 2.1. So it's just a smaller difference in electronegativity. Another way you could represent that is you could say, well, in my nitrogen-hydrogen bond, of course, nitrogen is more electronegative, so it's going to take more of the negative charge, and I'll put a delta minus by that. But with the oxygen-hydrogen bond, you can think about it as just being a bigger delta minus and a bigger delta plus because the dipole is simply stronger because, again, oxygen is more electronegative than nitrogen. And this picture down here is showing a ball and stick diagram of hydrogen bonding with methylamine. So I'll draw a partially condensed structure here where I show the nitrogen-hydrogen bonds, and you can see there's hydrogen bonding. I could even draw in another hydrogen bond to this molecule of methylamine. And lastly, on this slide, we have some interesting food for thought down here, which is tertiary amines cannot hydrogen bond. So there's no hydrogen bonding in tertiary amines, and there's a good reason for that. So let's say I had a tertiary amine like trimethylamine, and you've probably already figured this out. The reason that there's no hydrogen bonding between two molecules of trimethylamine rather, is simply because there are no nitrogen-hydrogen bonds. And that is going to be reflected in the physical properties when we look at the difference in the boiling points of primary, secondary, and tertiary amines. And you can see that right down here at the bottom. We have propanamine, ethylmethylamine, and trimethylamine. They are all isomers of each other. They all have the molecular formula C3H9N, but you can see they have very different boiling points. If I look at that of propanamine or propylamine, which is a primary amine, and that of ethylmethylamine, which is a secondary amine, you can see the boiling points are 48.7 and 36.7 degrees Celsius respectively, which are both much higher than that of trimethylamine. And why would that be? And the answer is simply because we have nitrogen-hydrogen bonds in the primary and secondary amine, and therefore these two molecules can participate in hydrogen bonding. And of course, the tertiary amine has no hydrogen bonding. Another interesting trend seen here at the top, it's comparing propane, ethanamine, and ethanol. And all three of these compounds have molecular weights which are very similar. And you can see that propane, the alkane, has a very low boiling point. And that's because it only experiences London forces. It is a hydrocarbon, therefore it is a nonpolar molecule. But then when we get into ethanamine and ethanol, you can see the boiling points increase a lot. And the reason why that of ethanol is even higher than that of ethanamine is because of stronger hydrogen bonding, so stronger H bonding, which we explained on the previous slide. And again, that is because oxygen is more electronegative than nitrogen and creates a stronger dipole and therefore a stronger hydrogen bond. The last thing I'll point out is that generally speaking, amines have boiling points somewhere between that of alkanes and alcohols. I want to draw your attention to these three molecules in table 15.1, methylamine, dimethylamine, and trimethylamine. And you see that when we go from the primary amine, methylamine, to the secondary amine, dimethylamine, both are capable of hydrogen bonding because they both have nitrogen-hydrogen bonds. But the boiling point of dimethylamine is actually higher, and the reason why is because not only can it participate in hydrogen bonding, but it's a heavier molecule because it has two methyl groups instead of one. But look what happens when we go from dimethylamine to trimethylamine. Even though the molecule is getting heavier, you can see that the boiling point drops down. And the reason why is because there is no hydrogen bonding with trimethylamine, because it is a tertiary amine. Another trend that's important is this one here. If you look at ethylamine, propylamine, and butylamine, we saw a trend similar to this with alcohols, that when we have these primary amines, when the carbon chain gets longer and longer and longer, what happens? The boiling point is going to keep increasing because the molecules get heavier. Table 15.2 shows direct comparisons between alcohols and amines. So if you first look at methanol, which is CH3OH, and you compare the boiling point of methanol to methanamine, and both of these compounds have very similar molar masses, you see that the boiling point of the alcohol is much higher. It's 64.5 degrees Celsius. Why is that? Because the hydrogen bond in an alcohol is stronger than that in an amine. The same trends are also seen for a comparison of ethanol and ethanamine and propanol and propanamine, in that the alcohol always has a higher boiling point, again, because the hydrogen bond with an alcohol is stronger than that of an amine. Let's look at a problem here. It says which molecule in each pair will have the higher boiling point. So first let's look at methanol, which is CH3OH, and we'll compare it to methylamine, which is CH3NH2. And I bet you right away you know that methanol is going to have the higher boiling point, because although both molecules are capable of hydrogen bonding, the hydrogen bond in an alcohol is stronger than that in an amine. The next one is a comparison of dimethylamine. I'll draw the structure here, NHCH3, and we're comparing that to water, H2O. And the boiling point of water is going to be much stronger. And I explained that to you earlier on in the course, that water has the capability of maximizing its hydrogen bonding because it has two hydrogens, so two delta pluses, and it also has two lone pairs. Also, again, the dipole in the oxygen-hydrogen bond is stronger than that in the nitrogen-hydrogen bond. The next one is methylamine. I'll draw the structure, and we're comparing that to ethyl, so I'll draw an ethyl group, ethylamine, and you can probably guess that ethylamine is going to have a higher boiling point. They're both primary amines, but ethylamine has a longer hydrocarbon chain, so it's a heavier molecule. It's going to have more London forces in this portion of the molecule, and therefore it's going to have a higher boiling point. And the last one is propylamine. Let me draw the structure here. We put a propyl group, and then our amino group, or butane. Butane. And you can probably guess right away that propylamine is going to have a higher boiling point. And the reason why is because it is capable of hydrogen bonding, whereas butane is a hydrocarbon and only experiences the much weaker London forces. And so propylamine has a higher boiling point. In terms of solubility, it says that all amines can form hydrogen bonds with water. Even tertiary amines can form a hydrogen bond with water. And the reason why is because even though a tertiary amine doesn't have a nitrogen-hydrogen bond, it still has a lone pair. And the lone pair is capable of forming a hydrogen bond with water. I'll draw in my delta plus here, and I'll put my delta minus next to my lone pair. And again, although a tertiary amine cannot hydrogen bond in a pure sample by itself, it can hydrogen bond with water. We also see a hydrogen bond between the primary amine, methylamine, shown here, with a lone pair on water. And of course, we could represent hydrogen bonding the same way for a secondary amine. The next point says that amines up to 6 carbons long are generally water-soluble due to hydrogen bonding. And water solubility is going to decrease as the length of the hydrocarbon portion, and remember, hydrocarbons are hydrophobic, as the length of that hydrocarbon portion increases, the water solubility will decrease. And we saw the same thing with alcohols. The nomenclature of amines is a little bit involved in that we have to learn the nomenclature of primary amines and secondary and tertiary as well. But let's start with primary. And it says here that primary aliphatic, which means non-aromatic amines, are named by first finding the parent compound. So we find the longest continuous carbon chain that contains the amine group. Then we drop the final E of the parent name and we add amine. So for example, if you had ethane, it would become ethaneamine, propaneamine, butaneamine, pentaneamine, so on and so forth. Then you number that longest chain, the parent chain, in a way that you give the carbon that has the amino group attached to it, you give it the lowest possible number, and then you name and number all the substituents as usual, so 2-ethyl, 3-methyl, so on and so forth. So you can see here that we have methaneamine. You might remember that CH4 is methane. Methane, I hope you remember that. It's the simplest organic molecule. So methane, so we drop the E at the end and we add amine on the end, so methaneamine. The next one is 1-propaneamine, and the reason why we have a number in this one, so we say 1, 2, 3, the reason we call this 1-propaneamine is because there's also 2-propaneamine, and in fact I could draw the bond line structure for you. This would be 2-propaneamine. And then we have 2-pentaneamine, and of course the longest carbon chain is highlighted in yellow, and it's numbered in such a way to give the amine group, or what we call an amino group sometimes. The amino group is given the lowest possible number, which is the number 2. And so we call this 2-pentaneamine. Naming secondary and tertiary amines gets a little bit trickier, but still definitely doable. And it says here the prefix N-alkyl is added to the name of the parent for secondary and tertiary amines. So let's take a look at this first example right here. So the first thing we do is we find the longest carbon chain, and it's an ethyl group, right? So we would call it ethaneamine, okay? Now we also have this methyl group over here, which is smaller, and we use this N-alkyl prefix. So since it's a methyl group, we call it an N-methyl, and then you put it all together because when we have letters, the L and the E, we don't separate letters by anything. So it's going to be N-methyl ethaneamine. The same thing applies to a tertiary amine. like N,N-dimethylmethanamine. So here we have the longest carbon chain, which they could have put the yellow box around any three of these because they're all just methyl groups. But I have methanamine, and then I have N-methyl and N-methyl, so I call that N,N-dimethylmethanamine. So let's say you had this tertiary amine down here. You can see that the longest carbon chain has 4 carbons in it. So 1, 2, 3, 4. So the parent is butanamine, and I have 2 methyl groups on the end here. So this compound would be N,N-dimethylbutanamine. When we name aromatic amines, it says here that several aromatic amines have special IUPAC approved names. You only have to know aniline, and it's a good idea to know the toluidines. So aniline is just a benzene ring with an amino group on it. And we could call that benzene amine. That would be a correct IUPAC name, but generally speaking, chemists like to use the name aniline, which is a common name. And so you need to know the structure of aniline. It's a benzene ring with an NH2 group on it. Now you probably remember this molecule here. If I take a benzene ring and if I put a methyl group on it, it becomes toluene. So when I have a methyl group on my amino, it's called toluidine, and that's a common name. So if I have a 1,3 substitution pattern, I call that metatoluidine. If I have a 1,2 substitution pattern, it's called ortho. And if I have a 1,4 substitution pattern, of course, it's called paratoluidine. And the last point says that as additional groups are attached, they are named as N-substituted derivatives of aniline. And as an example of that last bullet point, if I draw this and I put 2 methyl groups on this nitrogen on my aromatic ring, how would I name this compound? Well, I have 2 methyl groups on my aniline molecule. So I would call this N,N-dimethyl Let's try another one. Let's say I had only 1 alkyl group on my aniline molecule. So let's say if I had an ethyl group on it. How would I name that? I would call this N-ethyl aniline. When dealing with small amines, common names are very often used by organic chemists. And the rules for common names are that first we name the alkyl groups attached to the nitrogen in alphabetical order, and then we just add the word amine at the end. So you can see that this is a much simpler way than the IUPAC way. It's very commonly used, right? The name is continuous with no spaces between the groups. So you can see that every single compound on this page, they all end with amine, right? That's the suffix for all of them. So this one has a methyl group, so we call that methylamine. This one has an ethyl group, so we call it ethylamine. We have 2 methyl groups over here, so we have to prefix that with di meaning 2. If we have 2 alkyl groups that are different, we have an ethyl and a methyl, we list them in alphabetical order, so E comes before M, so this compound would be ethylmethylamine. And if you have 3 methyl groups like this, we have to use the prefix tri meaning 3, and this is trimethylamine. And if we just think about trimethylamine, you can see why organic chemists love common names so much. It's a lot easier to say to somebody in the lab, could you pass me the trimethylamine, as opposed to, could you pass me the N,N-dimethylmethanamine? Although amines play many different roles in our day-to-day lives, one very important use is in medicine. A host of drugs derived from amines is responsible for improving the quality of life, whereas others, like cocaine and heroin, are highly addictive. Amphetamines, like benzedrine and mephedrine, stimulate the central nervous system. They elevate blood pressure and pulse rate and are often used to decrease fatigue. Medically, they have been used to treat depression and epilepsy. Amphetamines have also been prescribed as diet pills because they decrease the appetite. Their use is controlled by federal law because excess use of amphetamines can cause paranoia and mental illness. Many of the medicinal amines are analgesics or pain relievers, or anesthetics or pain blockers. Novocaine and related compounds, for example, are used as local anesthetics. Demerol is a very strong pain reliever. Ephedrine, its stereoisomer pseudoephedrine, and phenylephrine, also called neosynephrine, are used as decongestants in cough syrups and nasal sprays. By shrinking the membranes that line the nasal passages, they relieve the symptoms of congestion and a stuffy nose. These compounds are very closely related to L-dopa and dopamine, which are key compounds in the function of the central nervous system. Recently, many states have restricted the sales of products containing ephedrine and pseudoephedrine, and many drugstore chains have moved these products behind the counter. The reason for these precautions is that either ephedrine or pseudoephedrine can be used as the starting material in the synthesis of methamphetamines. In response to this problem, pharmaceutical companies are replacing ephedrine and pseudoephedrine in these decongestants with phenylephrine, which cannot be used as a reactant in the synthesis of methamphetamine. Ephedrine and pseudoephedrine are also the primary active ingredients in ephedra, a plant found in the deserts of Central Asia. Ephedra is used as a stimulant in a variety of products that are sold over the counter as aids to boost energy, promote weight loss, and enhance athletic performance. In 2004, the Food and Drug Administration banned the use of ephedra in these over-the-counter formulations after reviewing 16,000 reports of adverse side effects including nervousness, heart irregularities, seizures, heart attacks, and 80 deaths, including that of Baltimore Orioles pitcher Steve Betchler at age 23. Now let's talk about reactions involving amines, and we'll start with the preparation of both aliphatic and aromatic amines. And it says here that aliphatic amines are prepared via reduction of amides and nitro compounds. So you remember an amide functional group, and you remember also that when we want to show reduction in Chemistry 102 that we use a hydrogen atom inside these square brackets because in organic chemistry, reduction can be regarded as the loss of oxygen or the gain of hydrogen. And so when we add hydrogen to that amide, not only do we gain 2 hydrogen atoms, but we also lose this oxygen to produce an amine. And it says here that, of course, the R2 and R3 may be a hydrogen to produce a primary amine, or it could be an organic group. So this would work to produce a primary, secondary, or tertiary amine. And the way that aromatic amines are prepared is via a reduction reaction, but instead of reducing an amide, we reduce a nitro compound. So you should remember the nitro functional group that I have shown here. So we take this molecule, this is actually called nitrobenzene, and if we reduce that, we produce an aromatic primary amine. Of course, this is aniline that's shown here. So this is showing the reduction of nitrobenzene to produce aniline. And of course, you're responsible for knowing both of these reactions, the reduction of an amide to produce an amine, or the reduction of a nitro compound to produce an amine. On the first slide of this video, I mentioned that amines are bases. Now, they are not strong bases, they are weak bases. Strong bases are things like sodium hydroxide, potassium hydroxide, etc. Those are the kinds of bases that we talked a lot about in Introduction to Chemistry 1, but amines, they are bases, but they are weak bases. Now, what's the definition of a base? And you remember, hopefully, that the Bronsted-Lowry definition of a base is something that accepts a proton, H+. So amines accept protons when they are dissolved in water. And the way that that happens is the lone pair on the nitrogen atom can be shared with a proton from water. But what happens is that you end up producing what's called an alkylammonium ion, shown down here, and you also produce hydroxide. And when you put pH paper in a solution, what you're actually doing is measuring the concentration of hydroxide. And so that is why when you dissolve an amine in water, the reason the pH paper shows that the solution is basic is because the amine is accepting a proton from the water, producing the alkylammonium and what? Hydroxide. So you are forming a basic solution. Here's a specific example of methylamine, which is a primary amine. And I can even draw some arrows to help us out here. So I'm going to draw an arrow from the lone pair on the nitrogen to that hydrogen on the water molecule. And that curved arrow represents the formation of a bond. But remember, hydrogen cannot have 2 bonds. So as this new bond is forming that I've drawn here, represented by this red arrow, simultaneously there must be a bond breaking, right? These two electrons in this oxygen-hydrogen bond must have to move over to the oxygen to make the hydroxide ion. And of course, I produce the methylammonium ion when I do that. And so what's the take-home message of this slide? Is that when I put an amine in water, I produce hydroxide, which is basic, and I also produce, in this case, a methylammonium ion. Now, water is not a strong acid, but when I take an amine, which is a base, a weak base, and I treat it with an acid like hydrochloric acid, which is a strong acid, you can see that I have an arrow that's going in one direction. That means this is an irreversible reaction because the strong acid donates that proton completely to the amine to produce an alkylammonium salt. Notice that we're not producing hydroxide here, right? We're producing chloride as well as our alkylammonium ion. And if I went ahead and drew the complete Lewis structure of HCl just for illustrative purposes here, I could do the same thing that I did in the last slide where I show the lone pair from the nitrogen forming a bond with the hydrogen. But again, hydrogen cannot have two bonds. So simultaneously, as I'm forming that new bond, I'm going to break this bond. So I end up with my alkylammonium and my chloride, which has 4 lone pairs on it now. You might be wondering, how do we name alkylammonium salts? We name amine salts by replacing the suffix amine with ammonium. And you probably remember the ammonium ion from Introduction to Chemistry 1. I'll help you out here. Here's the ammonium ion. And then, of course, you add the name of the ion. And the reason why it's useful to make salts is because when we convert amines to salts, it often makes insoluble amines soluble, as salts, of course, are ionic. And we already looked at how to name this primary amine, methylamine. And when I make the ammonium ion, I convert amine to ammonium, so it becomes methylammonium. And then I just name my anion, which in this case is chloride, so I get methylammonium chloride. Alkylammonium salts can behave as weak acids, and they can neutralize hydroxide ions. They can neutralize the hydroxide ion. And when they do that, they end up forming water, because when we take a salt plus a base, we end up with an amine plus water. So what happens is the protonated amine, or the ammonium cation, converts into an amine. And it says here that this reversal of the alkylammonium salt to the amine is very important in many drugs. And so if I use that curved arrow nomenclature that I've used in the last couple of slides, my hydroxide is forming a bond with one of the protons from my alkylammonium salt. And simultaneously, I'm going to break this bond, and the 2 electrons are going to go onto the nitrogen to produce the amine and water. Quaternary ammonium salts are ammonium salts that have 4 organic or alkyl groups bonded to the nitrogen, and as a result, do not have an unshared pair of electrons. They have this general structure. Quaternary ammonium salts that have a very long carbon chain, sometimes called quats, are used as disinfectants and antiseptics because they have detergent activity. 2 popular quats are benzalkonium chloride, or Zephyran, and cetylpyridinium chloride, found in the mouthwash Scope. Choline is a very important quaternary ammonium salt in the body. It is part of the hydrophobic head of the membrane phospholipid lecithin. Choline is also a precursor for the synthesis of the neurotransmitter acetylcholine.